Sir, you have given that assignment, sir. In that assignment, I have the last problem. I was going through that problem, sir.
Can you be a little louder?
Sir, that assignment, whatever you posted, no, sir. I was going through that problem. Are you able to hear me, sir?
Go ahead again.
Yeah, sir. That assignment problem, what you have posted in assignment 8, I was going through that problem.
SMA problem.
Assignment.
Assignments. Okay.
Yeah.
Okay.
In that, sir, that you have given the 10th question, sir, that beam with bending as well as torsion.
Yeah.
Yes, sir. That 10th problem, sir. What that is supposed to be done by me.
Okay.
Sir, in that what I wanted to ask you, sir, that that 3-dimensional treatment I want to introduce in that. That's what is it? So how to approach that? I was.
A solid steel shaft of diameter D is subjected to bending moment and twisting moment.
Yes, sir.
Right. The two are given. Determine the ratio of tau max by Y. Y is yield strength.
Yes, sir.
The shaft. Y is the yield strength of the shaft. What does that mean? What does it mean to say yield strength of the shaft?
It is isotropic.
Isotropic.
What else? It's a shaft that I'm talking about. The shaft material yield strength is given. What does it mean to say yield strength?
Tau
when I do the tension test,
okay,
it will yield at the value of Y.
Yes, sir. Okay.
Understood?
Okay.
Yeah?
Yes.
Now, you have twisting moment and bending moment. What stresses will be created?
Torsional stresses and bending stresses.
Torsional stresses and
bending stresses.
And
normal and shear stress.
Torsional stresses are what kind of stresses?
They are shearing stresses. Shearing stresses.
Right? Shearing stresses, right? So if it is shearing stresses and bending moment will create?
Normal stress.
Normal stress.
Normal stress. So if I have to use normal stress, the stress tensor or matrix will be what? I have a beam like this. I have a shaft like this. It is twisted, right?
Yes, sir.
It is twisted. Let's say this direction is, tell me a direction.
1-1.
Huh? One direction.
One direction.
Okay. And let's say the other one is 2 direction and 3 direction. Okay.
3 direction. Yes, sir.
Now, what kind of stress will be developed due to torsion?
1, 3.
So on
Tau what?
1, 3.
Tau shearing stresses means tau 1 3, tau 1 2.
Which one?
Tau
2 3. Tau 2 3.
Yeah.
Tau 2 3.
Yes, sir.
Sure, huh?
About 1 we are rotating.
Sir, about 1 it is rotating, so it will be in
on what
direction
surface
of 2 and
will you see this stress?
On the face.
Sir, 2 3 sir.
On the
1, 2.
on
Tau
the face.
2 3 on the face.
I can't hear you. Somebody is.
Sir, tau 2 3 in the face.
Tau 2 3 is the face.
Yes, sir.
No, the face
Because
which is in the direction
what
of
is the
1.
normal direction of the face?
Sir, 1.
1.
1. So
One
one
is the
has
normal.
to appear in the shear stress.
Yes.
Right? So what would it be? Tau?
1 2 and 1 3.
1 2 and 1 3 or 1 2 alone or 1 3 alone, and its reciprocal, its conjugate, right? 2 1 or 3 1.
3 1.
Yes.
Right? Because it depends on where I take. On the face, if I take the face and if I take at this point, At
You
this
get tau
point,
23.
shear stress will be like this, correct?
Yes, sir.
Yes, sir.
Right? And the normal direction is 1, and this would be the 3 direction, correct?
Yes, sir.
Yes. So tau 13 will appear. On the other hand, if I take this, then it will be
Like
tau 12. Are you with me?
1, 2. Yes, sir.
Right. So what you do is you take one of those and write it down. So it will be tau 12,
Tau 1, 3.
tau 12. All the rest are 0. And due to bending, it will be just
Sigma 1.
Sigma 1.
sigma 1. Correct? Right? Normal to this phase. So the stress will be acting normal to this. Yes or no?
Yes, sir.
Yes, sir.
Supposing I plot it, it will be like this. Right? Got it, Subha?
Yes, sir, I got it. Sir, now henceforth we can carry
Beyond this, you have to explain to us.
Sir, in problem 9, can you just explain the question once, because I am having some doubts regarding how the pistons are placed. And
A solid soft aluminum cylinder, 100 mm dia and 150 mm long, is closely fitted inside a thick walled cylinder. Inside a thick walled cylinder.
okay, sir.
So one is a thick walled cylinder, the other is a solid cylinder.
Solid.
Are you with me?
Yes, sir.
Yes, sir.
Length is given to you. An axial load P is transmitted to the aluminum cylinder by means of 2 frictionless pistons. All right?
Sir, I had doubt in that. How are you transmitting the axial load? Exactly where is it fitted to the piston?
Oh, okay. That's the question you have. Basically, where is the axial load coming in? Correct?
Yes, sir.
Is that what you're saying?
Yes, sir. If you can draw a figure or something, I
So
think it will be.
just do one thing. Forget about all this frictionless cylinders, etc., etc.
Yes, sir.
Right now, the piston has to be inside, correct?
Yes, sir.
Right? And the axial load is delivered to the aluminum cylinder. Okay, you have a cylinder. Okay, let's say this is the thick walled cylinder.
Yes, sir.
Inside this is another aluminum cylinder.
1 second, sir. Dharmi, can you mute your this thing, because it's switching to your camera again and again.
Oh, okay.
Mute your mic. That's
Are you able to see me now?
Yes, sir. Now it's
This is the let us say this is the thick wall cylinder.
Yes, sir.
Inside you have snugly placed the solid cylinder.
okay, sir. Snug fit.
That aluminum cylinder, it just fits. Means
Okay, sir.
it is not transferring any stresses.
Yes, sir. Okay.
Now there is a piston, 2 frictionless from here and here.
Okay.
So aluminum rod is in between. Think of it as a rod, and 2 pistons are pushing this aluminum cylinder. So far, okay?
From both the sides.
Yes.
Okay, sir. So it's just pushing the aluminum part, not the whole system.
Yeah, but what happens is there is Poisson's ratio.
Okay. Okay. So what you're telling is while aluminum cylinder is getting pushed in, even the other cylinder will have some effect because of the
Correct.
fit.
Right.
So the force is getting transmitted to the thick cylinder
Right.
through the aluminum cylinder, not directly
They said,
from the
okay,
piston.
make the steel cylinder to be completely rigid. So it makes it easy for
Sir,
you.
isn't it kind of a confined kind of thing?
Yeah, it is a confined kind of problem where due to Poisson's ratio, it tends to expand. But when it tends to expand, the steel cylinder, so
Is rigid.
read it as closely fitted inside a thick wall steel cylinder. This is the steel cylinder. Okay.
Yes, sir.
Let's say this steel cylinder extends. There's a piston here.
Yes, sir.
There's a piston here. Okay.
Yes, sir.
This is delivering a force, whatever P. This is steel rigid. This is aluminum. Aluminum. So far, okay?
Yes, sir.
This push is P. Push or pull does not matter, so push. Due to Poisson's ratio, this would want to expand. But this steel cylinder is not willing to expand. Total length is given to you. So far, okay?
Yes, sir.
You can think of it like this, or you can think of it like this also. In which case, there is only one cylinder which is trying to push. You'd have seen some powder compaction, no?
Yes, yes, sir.
Yes, sir. Yes, sir.
Think of it like that.
So I have to
there is this thing, and there is a piston pushing it, let's say compacting it. In this case, instead of powder, I told you that it is an aluminum cylinder.
No, so I have to find the stresses induced, like.
Yeah, you can find the stresses induced and then apply the yield condition.
Okay, sir.
Tell when it starts to flow. That's what it is.
Okay, sir.
Sir, in my problem, third problem.
Dharmi.
Yeah, sir, third problem. Can you please?
Third problem.
In this, sir, we need to find out the yield stress using von Mises and Tresca criteria, right?
Yeah. And since the ends are closed, you will have two stresses coming into picture, hoop as well as longitudinal.
Yes, sir. Yes, sir.
That's it.
So I only have to
Apart
show
from
the
that,
von Mises.
there is also an axial load.
Yes, sir. Axial load. So we need to calculate that axial load only, right?
Yeah.
So, sir, there is von Mises criteria in Tresca. Only the difference is 0.5. Means that coefficient of 0.5 in Tresca and 0.57 in von Mises. So I only have to multiply with that, and I have to give
No. The 0.5 and all those you find out.
Oh, okay. So I have to.
Is given to you.
Okay.
What it is, you need to find out. Whether it is 1/2 or √3/2 and all those, you find the equivalent.
Oh, okay. So I have to derive the von Mises and Tresca criteria for
yield
this.
Stress is given to you. Yield stress is nothing but an axial tension. That is.
Yes, sir. Yes, sir.
Right.
Yes, sir.
Yield stress is given to you, and for this condition, what would be the load?
Okay, sir. Sure.
All right.
Yes, sir. Yeah.